Section. Introduction. We're here to talk about the recent advancements in large language models, LLMs, and other generative AI, GenAI, systems. These systems have shown remarkable success in various fields, from natural language processing to computer vision. However, there are concerns about their responsible use and deployment. These models, like their predecessors, can sometimes make mistakes or even create or hallucinate information. This issue of hallucinations has raised concerns about misinformation and over-reliance on the system's output, especially when it seems to be providing the correct answer. It's been observed through various studies that these hallucinations are not rare. Even everyday users, or citizen scientists, have reported a wide range of hallucinations while using models like ChatGPT on common web forums. Despite the growing number of studies on this phenomenon, there's no standard vocabulary or ontology for representing hallucinations. Having such an ontology and datasets modeled using it would be beneficial. It would allow us to better understand and categorize the different types of hallucinations. Without a common vocabulary, data collected on this phenomenon would be inconsistent and require significant manual work, making it more difficult to conduct systematic studies. We also need to ensure that any such ontology is practical, well-documented, and capable of modeling both hallucination instances and their metadata, which includes details such as which LLMs the hallucination instance was tried on, when it was tried, its origin, and so on. Preliminary evaluations show that not all LLMs hallucinate equally. There are clear differences between the major language models currently in use. With these considerations in mind, we propose the Hallucination Ontology, HALO, a resource for modeling hallucination instances and their metadata. We've designed HALO to be a sustainable and extensible resource for researchers studying hallucinations in GenAI models and LLMs. HALO has been designed following a rigorous process and supports multiple hallucination categories and subcategories, metadata fields, and attributes. It consists of two main modules, the hallucination module and metadata module, which allow us to maintain a clear separation between different hallucination types and concepts and properties that are better suited for capturing experimental data on hallucinations. We've demonstrated the utility of HALO using a set of competency questions that are similar to those normally studied in empirical studies of hallucination. We've used a real dataset on hallucinations collected from a diverse set of sources on the web, and shown that even relatively complex questions can be formalized as SPARQL queries using HALO concepts and properties. The advent of GenAI and large language models, LLMs, like ChatGPT and Bard mark a significant evolution from an earlier generation of models. These models are distinguished by their use of reinforcement learning in addition to deep transformer neural networks based on attention. Hallucinations have been recognized as a relatively new class of errors and false predictions in the context of GenAI. Hallucinations are not uncommon, and researchers have documented them in a diverse range of generative tasks, such as text summarization, text generation, multimodal problem solving, dialogue, question answering, and language translation. As we've learned more about hallucinations, their definition and scope has expanded. The evaluation of hallucinations in LLMs has transitioned to focus more on the distinction between factual reality, fabricated results, and the ability of LLMs to follow human instructions. Modern LLMs are considered superior compared to an earlier generation of language models like BERT. They can handle complex prompts and instructions, but this complexity has also resulted in more sophisticated hallucination patterns. Researchers are already trying to define and categorize hallucinations in LLMs in a rigorous way, but efforts are ad hoc and do not rely on the formal machinery that is a strength of the semantic web. Nevertheless, such works do offer insights into hallucination causes, types, and potential solutions, even though they do not always take into account the hallucinations published in non-academic sources. To the best of our knowledge, there is no existing hallucination ontology in the literature that has a formal representation. Recognizing this gap, we drew upon the linked open terms, LOT, methodology as our guiding framework. LOT's methodology is particularly suited to our goal of developing a robust, extensible ontology from scratch. Moreover, to connect hallucination in LLMs with existing classes and enhance interoperability, we also follow the minimum information to reference an external ontology term, MIREOT, guidelines. Beyond hallucinations, there are many resources and decades of related work in the semantic web on best practices for publishing ontologies expressing novel phenomena. Section Summary. The recent success of large language models, LLMs, and generative AI, GenAI, systems has raised concerns about their responsible use and the issue of hallucinations, where the models can make up or hallucinate information. This paper proposes the hallucination ontology, HALO, a resource for modeling hallucination instances and their metadata, to address the lack of a standard vocabulary for representing hallucinations. HALO is designed to be extensible, well-documented, and aims to facilitate systematic empirical studies on hallucinations in GenAI models and LLMs. Section: HALO, Design and Development. In this section, we'll discuss the design and development process of HALO, our ontology. We use the linked open terms, LOT, methodology, a common industry approach for creating ontologies and vocabularies. This method involves 4 stages: defining what the ontology needs to do, implementing the ontology, publishing it, and maintaining it. The LOT methodology also encourages reusing existing terms from other published vocabularies or ontologies. Before we delve into these 4 stages, let's first understand why we need an ontology like HALO. One of the main reasons is to standardize the way we describe and represent the various hallucinations discovered by a wide range of people, not just academics. These hallucinations are often shared online, particularly those related to popular language learning models, LLMs, like ChatGPT. These findings, often shared by journalists, tech enthusiasts, and others acting as citizen scientists, are valuable for research and for improving LLMs. However, because this information is scattered and lacks a standard vocabulary, it's not being effectively captured. HALO aims to provide this standard vocabulary. HALO can help answer questions like, do all LLMs hallucinate in the same way, or are there significant differences? What types of hallucinations are most common? And, with enough data over time, we could even determine if LLMs are getting better at handling certain types of hallucinations. When designing HALO, we considered 2 types of requirements. The first, functional requirements, were defined by competency questions related to GenAI hallucinations. We also created SPARQL queries for each question to validate HALO. The second type, non-functional requirements, included extensibility, interoperability, and maintainability. We designed HALO to be able to grow and adapt as we learn more about GenAI and its hallucinations. We also aimed for HALO to work well with other systems by linking each type of hallucination to external classes from existing vocabularies. Lastly, we wanted HALO to be easy to maintain, so we followed standard guidelines and created a pipeline to expand the categories of hallucinations and the scope of external classes. In developing HALO, we stayed true to the use cases and motivations we had initially outlined. We designed HALO to support a wide range of studies involving actual hallucinations, which led us to create 2 modules, the metadata module and the hallucination module. We used CHALP to create the initial conceptual model and Protégé to implement the OWL version. The design and development process of HALO involved many internal discussions to refine the ontology and meet the requirements we had set. We reviewed both data and literature to ensure that HALO included a basic set of hallucination categories and external entities. We also aligned our categories with common hallucination terminologies to keep our ontology current with the latest research and best practices. Finally, we evaluated HALO by asking for feedback and reviewing external knowledge, not just from academic literature but also from informal sources on the web. We created competency questions and corresponding SPARQL queries to fully validate the ontology. Through this iterative process, we refined HALO to its current version, the OWL version of which is provided in the resource links included with this paper. Section Summary. The section describes the design and development process of the HALO ontology, which follows the linked open terms, LOT, methodology. HALO serves as a standardized vocabulary and model for representing hallucinations discovered by various individuals, including non-academic scholars. The ontology implementation of HALO consists of 2 modules, the metadata module and the hallucination module, and it was refined through iterative discussions, literature review, and alignment with existing terminologies. The ontology also incorporates competency questions and SPARQL queries for validation. Section: Linking external vocabularies. We've developed HALO, a system that's based on 2 main sources: hallucination categories and external classes or entities. Our main goal is to ensure that HALO can work seamlessly with other systems. Here's how we did it. First, we identified the main types of hallucinations that are seen in language models by reviewing existing literature. These categories form the basis of Halo's hallucination module. Next, we wanted to include related vocabularies to make Halo as comprehensive as possible. However, not all classes and properties in these vocabularies are relevant, and importing all of them would be too much work. So, we followed the MIREOT guidelines, which suggest that we only need to reference the essential information of an external concept. This way, we were able to integrate relevant external concepts without including unnecessary terms. We also made connections between external classes that might appear in actual hallucination instances. For example, if a language model hallucinates a fact about a person, we link that to our hallucination module. This ensures that the meaning of the hallucination is accurately represented. Halo is published under the OpenCC by 4.0 license in two formats: a machine-readable file and a human-readable document. The machine-readable file follows best practices for publishing ontologies, and is available on GitHub and Zenodo. The human-readable document allows for more discussion on how to represent hallucination categories and metadata. We used Widowco to document Halo, which creates a series of interlinked HTML pages that provide a human-readable version of Halo. This documentation is publicly available online, which helps us meet FAIR's findability requirements. As for maintaining Halo, we plan to keep an active GitHub issue tracker. This will allow users to report issues and suggestions. We also plan to launch a Google form that will allow users to report actual hallucination instances. This will help us collect and analyze data on hallucinations in a standardized and automated way. Halo is made up of two main modules, the hallucination module and the metadata module. We've defined different hallucination categories that Halo supports, based on evidence from popular language models like ChatGPT and Bard. We've included two main hallucination categories in Halo. The first is factuality hallucinations, which are errors in language model outputs that misrepresent real-world facts. These errors can be factual inconsistencies, where the model produces answers that contradict real-world facts, or factual fabrications, where the model produces responses that can't be verified by real-world information. The second category is faithfulness hallucination, which refers to outputs that don't align with user instructions. This can be instruction inconsistency, where the model doesn't follow the user's instructions, context inconsistency, where the model's output doesn't align with the user's context, or logical inconsistency, where the model's output contains logical contradictions. In conclusion, Halo is a comprehensive system that categorizes and documents hallucinations in language models. It's designed to be extensible and is published under an open-source license. Section Summary. Halo, the hallucination ontology, is created by integrating two primary vocabulary sources: hallucination categories and external classes, entities. The ontology ensures interoperability by selectively importing relevant external concepts and establishing connections between external classes and hallucination instances. Halo is published under an open license in machine-readable and human-readable formats, with plans for active maintenance and collaboration. It consists of two modules, the hallucination module and the metadata module, with defined hallucination categories such as factuality hallucinations and faithfulness hallucinations. Section: Hallucination module. Let's talk about the hallucination module, a key component of Halo, our system. This module is organized into classes that correspond to the categories and subcategories we've previously defined. One of its main features is that it uses terms from existing vocabularies, following linked data standards. The module's structure is hierarchical, meaning it's organized like a tree. At the top of this tree is the main class, LLM's hallucination, which branches into two main categories: factuality hallucination and faithfulness hallucination. The first category includes two subclasses, factual fabrication and factual inconsistency, while the second category includes three subclasses: logical inconsistency, instruction inconsistency, and context inconsistency. This simple structure allows us to add new categories and subcategories as our research progresses. The instances in this module represent specific hallucinated prompts and responses identified by a researcher or through methods like citizen science. These instances often involve real-world entities such as people's names, places, and documented events, which vary according to the user-generated prompts. We've also linked this module to external classes like FOF, person, FOF, document, schema, date, and schema, scholarly article. Next, we have the metadata module, which represents the core concepts and properties of the prompts and answers we've collected. This module includes four main concepts: generative AI, large language model, LLM's prompt, and LLM's answers. Generative AI refers to the types of AI agents that have shown hallucinations. Large language model describes instances of language models that exhibit hallucination. LLM's prompt and LLM's answer contain metadata about the collected prompts and the language model's responses, respectively. We've also ensured that Halo is technically sound. It's interoperable, meaning it can work with other systems, and we've imported 7 external classes into it. We've made it publicly available under an open license, and it can be viewed using any web browser or visualization tools. We've also validated it using a known ontology scanner tool called OOPS. Ontology Pitfall Scanner, and it passed with 0 pitfalls. Lastly, we've documented Halo using the Widoko wizard, making it accessible and understandable to a wide range of users. Section Summary. The hallucination module in Halo is the main module that contains classes for each category and subcategory defined earlier. It integrates with existing vocabularies and follows linked data standards. The module has a hierarchical structure encoded as a taxonomy, allowing for expansion as new hallucination categories emerge. The metadata module represents the core concepts and properties of the prompts and answers gathered, including information about the AI agents, prompts, answers, and their relationships. Halo's technical specifications include interoperability with external classes, indexing and availability of the ontology, logical correctness and validation using OOPS, ontology pitfall scanner, and comprehensive documentation accessible online. Section. Evaluation. In our study, we used Halo to analyze and evaluate instances of hallucinations in language learning models, LLMs. We gathered 40 prompts from various online sources, including Reddit, the New York Times, and OpenGov, which are known to trigger hallucinations in LLMs. We also collected relevant metadata, such as the specific LLM that produced the hallucination, the date it was found, and the source of the prompt. Our main goal was to determine if hallucinations are consistent across different LLMs. For instance, if a prompt causes a hallucination in one model, like ChatGPT, would it also cause a hallucination in another model, like Bard? To answer this, we needed a diverse dataset of prompts, hallucinations, and LLMs. We initially tested the hallucinations on 3 different LLMs: ChatGPT, version 3.5, Bard, and Claude. These models are currently at the forefront of language-based AI research. ChatGPT, developed by OpenAI, is known for its conversational abilities and general knowledge. Bard, developed by Google AI, uses a unique attention mechanism to capture long-range dependencies in the input text. Claude, developed by Anthropic, learns from human feedback and conversations and is designed to be more introspective and aligned with human ethics. However, not all prompts were evaluated on all 3 models. To fully utilize Halo, we ran all 40 prompts on each model, resulting in 120 data points. This allowed us to confirm that a hallucination was indeed a hallucination and to pursue our main objective. Our preliminary analysis showed that Bard had the highest hallucination rate at 62.5%, followed by ChatGPT at 42.5% and Claude at 40%. Bard's higher rate might be due to its inability to refuse to respond to user prompts. These confirmed hallucination instances form the basis for evaluating Halo. We evaluated Halo using established guidelines. Our main goal was to show that Halo can model a variety of hallucination types and support a wide range of analytical queries. We created a set of competency questions, CQs, to guide our evaluation. For instance, we expected the answer to CQ1 to be that LLMs exhibit hallucination, and the answer to CQ2 to be that the factuality hallucination type is the most common. To conduct the evaluation, we translated the CQs into formal SPARQL queries using the concepts and properties in Halo. We found that Halo performed perfectly across all test cases, showing that it is rich enough to express the CQs as SPARQL queries and that it has been correctly implemented. We also ran a complex SPARQL query to verify CQ5, which involved comparing the hallucination abilities of different LLMs. We ran this query over 60 hallucination instances and created a confusion matrix to show the pairwise association between the hallucinations of different models. For example, the first row shows that there are 9 common prompts on which both GPT 3.5 and Claude hallucinate. In the future, as we collect more instances of hallucination classes and expand our dataset, we will be able to conduct even broader analyses using a set of CQs modeled in the same way as CQ5.